Okay, so the previous presentation on exponential functions, after all the stuff that we had done on complex differentiation, actually felt very much like an algebra class with a bit of calculus thrown in. That's going to continue at least for this presentation, because this presentation is going to feel like a trig class with complex numbers and a little bit of calculus thrown in. That's probably a good change of pace. Things are going to be nice and computational, and well, I double-checked these slides real carefully, so I hope we will not have that many mistakes. In fact, I hope we won't have any mistakes in this one. So let's go. Trigonometric and hyperbolic functions, of course, that is a subject that we already know because we have worked with trigonometric and sometimes also with hyperbolic functions before. But, well, how do we haul this over to the complex numbers? What do we know? For real numbers theta, we have that e to the I theta is cosine theta plus I sine theta. That was the very definition. If we replace theta with negative theta, we obtain that e to the negative I theta is cosine theta minus I sine theta. And that's because, well, the cosine is even and the sine function is odd, right? Okay, so if we add the two and divide by 2, well, that would mean if we add them, the imaginary parts go away. We get 2 cosine theta. If we divide by 2, we get cosine theta. And on the other side, we get e to the I theta plus e to the I minus theta divided by 2. And similarly, if we subtract the 2, that would mean that the cosines go away and we get 2i sine theta. And if we then divide by that 2i, we get that sine theta is equal to e to the I theta plus e to the minus e to the negative I theta divided by 2i, just as written here. Okay, and even though these are now identities that we have just proved for theta being a real number, the right-hand sides of these identities actually make sense for all complex numbers. And so that means for any complex number z, we will define the cosine of z to be e to the I z plus e to the I minus z, e to the minus I z divided by 2. And we will define the sine of z to be e to the I z minus e to the negative I z divided by 2i. And this time around, all the common identities carry over. So sine of z1 plus z2 will still be sine z1 cosine z2 cosine z1 sine z2. Cosine z1 plus z2 will be cosine z1 cosine z2 minus sine z1 sine z2. Sine squared plus cosine squared will still be 1. The sine will still be 2 pi periodic. The cosine will still be 2 pi periodic. And it turns out, well, now of course comes the big thing, right? In a class like this, we want to prove everything we claim. Now, we're not going to prove all those identities. We're just going to give a sample, and I think some identities are also supposed to be proved on the homework. But some proofs actually turn out to be simpler. For example, remember the additive identity for the sine. In calculus or trigonometry, if it was proved at all, it of course went back to the connecting to angles, and it was a geometric proof, and it was a good geometric proof, and in fact that's the proof that tells us that these functions, or proofs like this, are what tells us that these functions really do connect to trigonometry, to the investigation of triangles. But in terms of computations, of course, that proof was rather nasty. Now let's take a look at the right-hand side of the additive identity for the sine, which is right here, and let's see what we can do with this. Well, we do know sine of z1 is e to the I z1 minus e to the negative I z1 divided by 2i. Similarly, cosine z2 is e to the I z2 plus e to the negative I z2 divided by 2. Cosine z1 is e to the I z1 plus e to the negative I z1 divided by 2. And sine z2 is e to the I z2 minus e to the negative I z2 divided by 2i. And we can just multiply that out. And when we do that, we realize, well, there is a common denominator, 1 over 4i, right? And then if we multiply out the first one, we get e to the I z1, e to the I z2, which is here. We get e to the I z1, e to the negative I z2, which is here. We get minus e to the negative I z1, e to the I z2, which is here. And we get minus e to the negative I z1, e to the negative I z2, which is here. And we do the same thing in the second set of parentheses. We get e to the I z1, e to the I z2, which is here. We get e to the I z1 times negative e to the negative I z2, so that gives us a negative sign, and the z1 minus z2 here. We get e to the negative I z1, e to the I z2, which is here, and we get minus e to the negative I z1, e to the negative I z2, which is here. Okay, then we realize there are certain things that ought to cancel, right? This guy and this guy and this guy and this guy will cancel, and this guy and this guy double up, so we get 1 over 4i 2e to the I z1 plus z2 minus 2e to the negative I z1 plus z2. Well, we cancel the 2's and realize that that's e to the I z1 plus z2 minus e to the negative I z1 plus z2 divided by 2i, and that's the sign of z1 plus z2. And computations like these are in fact why many people like to work with the complex definitions of the trigonometric functions. Because if you have a really complicated trigonometric expression, it is often in fact easiest to replace all the sines and cosines with their exponentials. That might actually make the expression look even worse than before, but after that it's all algebra. You just multiply things out, you work with complex powers, and so on and so on. And hopefully, ultimately, it'll simplify down to a simple trigonometric expression. That is often easier than trying to find patterns, such as the additive pattern for the sine of z1 plus z2 in a really complicated expression. Okay, other proofs stay the same. For example, the sine of z plus 2 pi, the fact that that's the sine of z, well, we just use the additive identity, right? That's sine of z cosine 2 pi plus cosine z sine 2 pi. Sine 2 pi is 0, cosine 2 pi is 1, so that's sine z, and that's it. Okay, well, typically the philosophy often, and certainly my philosophy, is that sine and cosine are basically enough. Every so often we certainly will use the tangent, but we will reduce the tangent to sine z over cosine z when we have to do computations. The cotangent already becomes something that is fairly rarely used, and it's cosine z over sine z, just as it was defined on the real line. And then we also have secant and cosecant. Those definitions don't change. And it should be noted that secant and cosecant, at least around the world, are not very common. I think they are very, very much prevalent in English-speaking curricula, anything that's influenced by British or American curricula, but curricula in, say, Germany, for example, don't really worry about secant and cosecant, and, well, Germany still does pretty good engineering and mathematics, so maybe there's something to that. It's one of those, whenever you need them, use them or look them up, but I wouldn't worry too much about these functions. Okay, once we've got these functions, I mentioned at the beginning we have some calculus thrown in. Well, let's take a look at the derivatives. Well, the derivative of the sine function is the derivative of e to the iz minus e to the negative iz divided by 2i, and when you take the derivative of that, you get I e to the iz minus I e to the negative iz, and so then of course the minus minus becomes plus. We realize the i's cancel, so that's e to the iz plus e to the negative iz divided by 2, and that's the cosine of z. And similarly, the derivative of the cosine is the negative sine. So those are the same formulas as in calculus. And then the derivative of the tangent you get with the quotient rule, and it's 1 over cosine squared. The derivative of the cotangent is negative 1 over sine squared. I know you probably have learned these in calculus, or you may have learned these in calculus as secant squared and negative cosecant squared. I prefer to work with sine and cosine. And then, of course, the derivatives of the secant is secant times tangent, and once we deal with secant, we might as well deal with secants all the way through. The derivative of the cosecant is negative cosecant cotangent, and again, secant and cosecant, I really wouldn't lose much sleep over those. Okay, so that gives us the trigonometric functions. Well, the hyperbolic functions now look like a cheap trick. It's basically looking as if we just dropped the i's. For any complex number z, we can define the hyperbolic cosine to be e to the z plus e to the negative z divided by 2, and the hyperbolic sine to be e to the z minus e to the negative z divided by 2. That's the same thing as what we had before, only that we dropped all the i's. And if that was all there was to these hyperbolic functions, then I don't think anybody would worry about them terribly much. But it turns out the hyperbolic cosine is the solution to the differential equation that models a hanging chain. And so that means that this is something that does arise in applications. The other thing that happens is that the hyperbolic sine and the hyperbolic cosines are needed, well, their inverses are needed to solve certain kinds of integrals. That's also where ever so often you encounter the inverse secant and the inverse cosecant. So that's basically two reasons why the hyperbolic functions are important, and one reason given a little bit belated as to why sometimes people also work with secant and cosecant. Okay, note. Yeah, let's make the connection to the regular trigonometric functions. If we're looking at sine of iz, well, that's e to the iiz minus e to the negative iiz, and I times I is, of course, -1, so this becomes e to the negative z minus e to the z divided by 2i. Well, pull a negative sign out and realize that a negative sign is I times I, and then cancel one of the i's, and you realize that sine of iz is I times the hyperbolic sine of z, or sinh, as people sometimes also call this function. And the cosine of iz, same computation, actually a little simpler, turns out to be the hyperbolic cosine of z, and that thing is also often called cosh. Okay, another connection between sine and hyperbolic sine affects the absolute values, and that's going to be important as we're investigating the complex sine function, namely the absolute value of sine z quantity squared. What is that? Well, that's sine x plus iy times the complex conjugate of sine x plus iy. Now we use the additive identity, so that's sine x cosine iy plus sine iy cosine x, and of course I could have put the same thing here also with a bar on top. I think I didn't do that because this whole computation barely fit on one panel, but we know that this is the same thing only with a bar, so it's not going to be too hard to change later on. So we know now here that the first term, by what we had on the preceding slide, this is sine x cosh y, and this is I sinh y cosine x, and then we have times its complex conjugate, which is of course the same thing as what we have up here, only that the plus between real and imaginary part is replaced with a minus. And now we multiply that out, and we get, well, we get that the imaginary parts cancel, and we get therefore that this is the sum of the square of the real part, sine squared x cosh squared y, and the square of the imaginary part, which is sinh squared y cosine squared y. And now we're going to expand that a little bit, because now we can just add and subtract sinh squared y sine squared x, and subtract also sinh squared y sine squared x, and we see why we're going to do that in just a minute, because now we can factor out a sine squared out of the first and the fourth, and we get sine squared cosh squared y minus sinh squared y. And out of the middle we can factor out sinh squared y. So we get sinh squared y cosine squared x plus sine squared x. Well, we know cosine squared x plus sine squared x is equal to 1, which is good. And it turns out, you can verify that fairly easily, that cosh squared y minus sinh squared y is 1 also. So that means this is just sine squared x plus sinh squared y. So that expresses the absolute value of the square of sine z in terms of x and y and trigonometric and hyperbolic functions. And that's going to be very helpful for our next theorem, which says that the only zeros of the complex sine function are the numbers in pi, where n is an integer. We already know that for the real sine function this is true, and what this theorem therefore says then is that as we extend the sine function to the complex plane, there are no further zeros being picked up. And the proof, well, the only solutions of sine z equals 0 are the solutions of sine absolute value squared being equal to 0. Sine z absolute value squared is sine squared x sinh squared y when z is x plus iy. And in order for that to be 0, both of these squares have to be 0 because these now are real numbers because we have real inputs. And that means, well, the sinh is only equal to 0 at 0, so y must be equal to 0, and x must be equal to n pi because the real sine function is only 0 at n pi. And that means z equals n pi, where n is an integer, are the zeros of the sine function. No more and no fewer. Okay. The hyperbolic functions then, just like the regular trigonometric functions, also satisfy hyperbolic identities that are very similar to the trigonometric identities that we already know. Namely, well, the derivative of the sinh is the cosh, and the derivative of the cosh is the sinh. So in some ways, the hyperbolic functions are actually more cooperative because you don't have that many pesky negative signs flying around. Sinh z1 plus z2 is sinh z1 cosh z2 plus cosh z1 sinh z2. And cosh z1 plus z2 is cosh z1 cosh z2 plus sinh z1 sinh z2. So again, those pesky negative signs that we have to remember from the regular trigonometric identities are not present for the hyperbolic identities. So one way to memorize those is to realize that these things work just the same way, at least for these first four identities, as the regular trig identities, only that all the negative signs are gone. However, it doesn't, of course, keep going like that, and it turns out cosh squared z minus sinh squared z is equal to 1 rather than plus, as it is for the regular trigonometric functions. Whereas the regular trigonometric functions are 2 pi periodic, the sinh as well as the cosh are 2 pi I periodic. I think that makes a good bit of sense because if you add 2 pi I in the arguments of those exponentials, you just end up with an extra factor 1, which is not a problem. And there are more identities. We're not going to worry too much about them, and all of those identities can be verified straight from the definitions, just like we proved, for example, the trigonometric identity for sine z1 plus z2. You would here use the hyperbolic definitions on the right-hand side, simplified, and end up with sinh z1 plus z2. Okay, what else do we have? The only zeros then, yeah, sure, we can translate things that we know for the regular trig functions to the hyperbolic functions. So, for example, the only zeros of the complex hyperbolic sine function are the numbers n pi I, where n is an integer. And that's because sinh z is negative I sine iz. So this is equal to 0 wherever iz is equal to n pi. So that's equal to 0 wherever sine iz is equal to 0. So those are the zeros. Z equals n pi I. Actually, it's n pi divided by I and then negative n pi I. But because n is an integer, the negative sign can be absorbed in here. Okay. Of course, there are not just the hyperbolic sine and the hyperbolic cosine, even though those two rightly deserve most of the spotlight. We also have a hyperbolic tangent, which is defined just like the regular tangent. We've got a cotangent defined similar to the regular cotangent, a hyperbolic secant, as well as a hyperbolic cosecant. And again, hyperbolic secant and cosecant, I would not lose too much sleep on them. If you ever need them, look them up. If you ever need their inverses, look them up. But the main thing really is be very familiar with sine, cosine, and tangent, be they trigonometric or hyperbolic. Okay, the derivatives of those things, well, the derivative of the hyperbolic tangent is 1 over cosh squared. The derivative of the hyperbolic cotangent is negative 1 over sinh squared. So again, we've got very similar identities here. And then the derivative of the hyperbolic secant is negative hyperbolic secant times hyperbolic tangent. The negative derivative of the hyperbolic cosecant is negative hyperbolic cosecant times hyperbolic cotangent. And again, secant and cosecant, okay, that it is one of my soapboxes. Secant and cosecant, they really aren't that widely used. If you ever need them, look them up. Okay, Now we go to the inverse functions, and those inverse functions, of course, in trigonometry were important to work out certain angles, but we never really talked about how they could be computed, and our complex analysis has an answer for that, and that is nice. And then, of course, also these inverse functions are nice because through their derivatives, they are quite important in solving certain integration problems. So, for all complex numbers z, I claim that the arc cosine of z, the inverse cosine of z, is negative I logarithm of z plus I 1 minus z squared to the 1/2, where the right side is a multivalued function, which is of course sensible because the cosine hits every value between -1 and 1 infinitely many times, and if I remember correctly, the cosine hits every complex number infinitely many times. Don't pin me down on that right now, but it seems to be the case here. Yeah, from the formula for the derivative for the inverse function, I think we can see that already, because this thing is defined for all complex numbers, and so that ought to all work out. And well, here's where you can also see why you never were given a formula for the arc cosine in calculus. Calculus is occupied with functions of a real variable and then throwing all these imaginary numbers around, not to mention where those came from, as we're going to see in the proof. That would have been way too much overhead. Okay, what's the proof? Well, the inverse is always obtained by solving the equation w equals, well, the inverse is w equals arc cosine of z, and we can obtain an expression for the inverse function by now just solving for z. So we have cosine of w being equal to z. Well, okay, solving for w, and how do you solve for w? This is already solved for w. Well, we realize that this is the same as cosine of w equals z. And we now know, which we didn't know in calculus, that cosine of w is e to the iw plus e to the negative iw divided by 2. Okay, so we multiply by 2, bring that over, we get e to the iw minus 2z plus e to the negative iw equals 0. If we now multiply with e to the iw, we get e to the iw squared minus 2z e to the iw plus 1, and that's a quadratic in e to the iw, which means we can solve that with the quadratic formula. We get e to the iw 1, 2 being 2z negative b plus minus square root of b squared 4z squared minus 4ac. Well, it's actually not just 1, 2, because now the square root function actually is multi-valued. So let me fix that real quick. And we're back. So it's e to the iw being this expression where now already the square root symbol basically tells us that there are multiple values here. Well, that's z, because we divide by 2, plus minus square root z squared minus 1, because we took out the square root of 4. And that gives us w being 1 over I logarithm z plus minus square root z squared minus 1. And that is negative I logarithm z plus minus I times square root 1 minus z squared. And that is what we wanted to have. Let's make sure of that real quick. That's actually a plus here, and that is because as we go through the whole thing, the multiple values of the square root function now actually incorporate the plus minus. So for every positive solution of the multiple valued square root function, we end up with a positive and a negative value. I kept the plus minus in here because the square root notation really is reminiscent from the real line, and so this is more familiar to us. But as soon as we go to 1 minus z squared to the 1/2, that thing picks up all the solutions, and then we don't need the plus minus. Okay, similarly we can derive that the arc sine of z is negative I log iz plus 1 minus z squared to the 1/2. Again, when we solve that, we get a plus minus, but because the 1/2 picks up all the values, we don't need the plus minus. The arctangent is I over 2 log I plus z over I minus z. The arc area sine hyperbolicus. Area, not arc here, that's just the Latin root and the Latin background of that word is this. The inverse hyperbolic cosine is this. The inverse hyperbolic tangent is that. And no, do not try to memorize these formulas. What you want to know is how to derive them. If you ever really need them, better look them up. There's too many negative signs that could be lost here. Okay, the derivatives then, well, the derivative of the arc sine is 1 over 1 minus z squared to the 1/2, which then again is that multivalued function. And the proof is quite simple. You take the derivative, which means you take the derivative, of course, of the expression that you have for the arc sine. And when you do that, well, you keep the negative I. The derivative of the logarithm is 1 over whatever is inside, which is exactly what we have here. Then we have to multiply with the derivative of the inside. Well, the derivative of iz is I. The derivative of anything to the 1/2 is 1/2 of the anything to the negative 1/2, so 1 over 1 minus z squared to the 1/2. And then we still have the derivative of the inside, which is the negative 2z. And now we can cancel the 2's here and put the I on a common denominator. So we get negative I times the term in front is this. And then we have I times the denominator here minus z. And we realize now negative I times negative z is iz. And negative I times this thing is negative I squared, which is just 1 times 1 minus z squared to the 1/2, which is this thing. So that means the numerator cancels against this part of the denominator, and the derivative is 1 over 1 minus z squared to the 1/2. Again, a formula that we certainly remember from calculus for functions of a real variable. And similarly, all the other differentiation formulas stay the same. The derivative of the arc cosine is negative 1 over 1 minus z squared to the 1/2. The derivative of the arc tangent is 1 over 1 plus z squared. And that is already it. You can also work out the derivatives of the inverse hyperbolic functions. Basically, all these computations do go just the same. And of course, that's me waving my hands quite a bit. Some of the computations you will be doing on the homework just to really drive home the point and to make you confident into these statements that things just work the same. And for a lot of this other stuff, really, even though, of course, we want to at least be able to prove these formulas, when we need these formulas in an application, we will look them up. Don't try to memorize all those. Okay, that's it for this one. I think we are done with our complex trigonometry and with our complex algebra, at least for a little while. We're now going to start talking about integrating complex functions over intervals and the long paths. I'll see you in that one. Thank you. That means for any complex number z, we will define the cosine of z to be e to the I z plus e to the I minus z, e to the minus I z divided by 2. And we will define the sine of z to be e to the I z minus e to the negative I z divided by 2i. And this time around, all the common identities carry over. So sine of z1 plus z2 will still be sine z1 cosine z2 cosine z1 sine z2. Cosine z1 plus z2 will be cosine z1 cosine z2 minus sine z1 sine z2. Sine squared plus cosine squared will still be 1. The sine will still be 2 pi periodic. Okay, so the previous presentation on exponential functions, after all the stuff that we had done on complex differentiation, actually felt very much like an algebra class with a bit of calculus thrown in. That's going to continue at least for this presentation, because this presentation is going to feel like a trig class with complex numbers and a little bit of calculus thrown in. That's probably a good change of pace. Things are going to be nice and computational, and well, I double-checked these slides real carefully, so I hope we will not have that many mistakes. In fact, I hope we won't have any mistakes in this one. So let's go. Trigonometric and height cosine theta. And on the other side, we get e to the I theta plus e to the I minus theta divided by 2. And similarly, if we subtract the 2, that would mean that the cosines go away and we get 2i sine theta. And if we then divide by that 2i, we get that sine theta is equal to e to the I theta plus e to the minus e to the negative I theta divided by 2i, just as written here. Okay, and even though these are now identities that we have just proved for theta being a real number, the right-hand sides of these identities actually make sense for all complex numbers. And so cosine will still be 2 pi periodic. And it turns out, well, now of course comes the big thing, right? In a class like this, we want to prove everything we claim. Now we're not going to prove all those identities, we're just going to give a sample, and I think some identities are also supposed to be proved on the homework. But some proofs actually turn out to be simpler. For example, remember the additive identity for the sine. In calculus or trigonometry, if it was proved at all, it of course went back to the connecting to angles, and it was a geometric proof, and it was a good geometric proof, and in fact that's the proof that tells us that these functions or proofs like this are hyperbolic functions. Of course, that is a subject that we already know because we have worked with trigonometric and sometimes also with hyperbolic functions before. But, well, how do we haul this over to the complex numbers? What do we know? For real numbers theta, we have that e to the I theta is cosine theta plus I sine theta. That was the very definition. If we replace theta with negative theta, we obtain that e to the negative I theta is cosine theta minus I sine theta. And that's because, well, the cosine is even and the sine function is odd, right? Okay, so if we add the 2 and divide by 2, well, that would mean if we add them, the imaginary parts go away. We get 2 cosine theta. If we divide by 2, we get